Hi, in this video we will learn about length and distance of vectors in Rn, and then we will study the properties of length and especially the inequality called triangle inequality. Okay, so let's see what happens in the case of R2. If I have a vector in R2 and if I put it in the standard position, means that put its tail at the origin, then what happens in that case is that the head of this vector, the point, will have the same coordinates as the components of the vector. In other words, if this is u, OU is same as OA, that means that it is in the standard position. Then the vector will have components A and B. I'm writing the column form, but that's the same thing. If that's the case, well, we know that now if I draw this right triangle, this part is x component of A, which is the first component of the vector, and length of this side is second coordinate of A, which is the second component of the vector. We'll use the Pythagorean theorem, and you get that the length of u is a squared plus b squared. Find the square root of that. And while a little bit more we can do, in the video for the dot product, we saw that a squared plus b squared actually can be written in terms of dot product of a, b with itself. You see, the first component to first component is a squared, and second component to second component is b squared. Add them, and that means that we found the dot product of these two, well, u by itself, and then find the square root. Well, this is how we will define in general definition. Let u, which is a vector with n component, be a vector in Rn. The length of the vector u, how do we denote it? Denoted by length of u, we denote it by double lines. Put u in double lines, and that is how we denote it. And it's given by, well, now you know that this, we are going to define it as a square root of u dot v. And well, that will tell me that this guy is first component is squared, second component is squared, and add all of them up to the nth component square. Well, that is the definition of the length, and we will use that formula. Okay, let's do some examples. Well, just quick ones. Example, find length of given vectors. First one is a vector in R2, -1 to -2. And then the second one is a vector in R4, -3, 0, -1, 5. And we have to find their length. Okay, so length, the notation first, is equal to square root of score each component of the vector and then add them. This gives us, oops, I forgot that one. This gives us 1 plus 4 plus 4, which is root 9, and that is just number 3. The length of this vector u is 3. The second one, length of v, doesn't matter in how many components we have. The definition is the same thing. Square root of u dot u. U dot u, depending on how many components we have to add the square of those components and then find the square root to find the length. So it will be negative 3 squared plus 0 squared plus negative 1 squared plus 5 squared. Well, this gives us 9, 0, 1, 25, and that is root 35. Okay, so that's an example. Before we go to the properties, let me define the distance, but where the distance of two vectors come from. Well, this is how you compute the distance of two vectors. Basically, distance in R2, distance, this is actually in general, distance of two vectors in the standard position. So first put their tail or initial points on the origin. Standard position is equal to the distance of their end points. There, maybe I should have written terminal points. Terminal points. Well, what does it mean? It means that, okay, I have a vector u here, vector v here, and the distance of these two vectors, so let me write distance of u and v is equal to the distance of the end point, the terminal point of these two. So distance of points A and B. Yes, so you find the distance of these two, and that's how you get the length. Okay, then well, we have somehow some way to formulate this length or the distance of the points A and B. Remember that vector u minus v is that side of that vector, while the direction goes from this side to that side. So the distance of points AB is then same thing as length of u minus v, and that's how we define it. So definition, distance of two vectors u and v in Rn. Well, how do we denote it? Denoted by d of u v is given by u, d of u and v is equal to length of u minus v. So you find u minus v, and then the length given by that u minus v is what we call it the distance. That's the second formula of this video. So let's do some examples. Example, find the distance of given pairs of vectors. Okay, first one, I have two vectors here from R2, 1, 2, and 5, negative 1. So let me call this U, let me call this V. And then the second one is two vectors from R4. What are the vectors? 0, negative 1, 2, or actually not 0, okay. Negative 1, 2, 1, and 2. And V is 3, 0, 1, and negative 2. Very nice. So let's just compute this thing. We know that distance of U and V is the length of U minus V. And we do the subtraction, vector subtraction component wise. So this is 1 minus 5, 2 minus negative 1. This gives us negative 4 and 3. Don't forget to put the length sign, so the length sign in here. And we know that the length is square each component and add them. So this is 16 plus 9, this is root 25. And as a result, the distance is just 5. Distance of these two vectors is 5. How about distance of UV in this case? Distance of UV. Well, we need first to find U minus V, negative 1, 2, 1, 2, minus 3, 0, 1, and negative 2. And this is, do it component-wise. 2 minus 0, 1 minus, 1 minus 1, and then 2 minus negative 2. Length of that, this is equal to length of negative 4, 2, 0, and 4. Nice. Well, square each component, negative 4 squared plus 2 squared plus 0 squared plus 4 squared. And that gives us 16 plus 4 plus 0 plus another 16. 16 plus 16 is 32, plus 4 is 36. Root 36 is just 6. So we found the distance of these two vectors, which is equal to C. So that was the second thing for this video. And the last thing is finding the properties, studying the properties of length. When it comes to properties of length or anything from this point on about the vectors, you have to first study how that new object or new notion works with the vector operations. So these four things will be related to that. So first thing is that, okay, so this is something we proved. The length of a vector is 0 if and only if the vector itself is 0 vector. In other words, all vectors will have non-zero length unless that vector is equal to 0 vector. Well, why this is true? This is the result of this fact. You remember that we showed that u dot u is 0 if and only if u is a 0 vector itself. And remember now that the length of u is square root of u dot u. And that's how you prove that part. The second thing is that how length and scalar multiplication work. We had the discussion about the scalar multiplication. When it comes to scalar multiplication, length of cu is always c times length of u if c is positive number. If it is negative number, you have to put absolute value of c. So this is the notion, the geometric interpretation of the scalar multiplication we discussed in details what is happening. But one can ask for proof. Yes, we can prove that this fact just by following the definition. So un, this guy, first make it one vector, so scalar multiplication, c is multiplied to all the components of u, and then we find square of each one, and then find the square root. When we do this, what we notice is that, okay, each one of these guys, we can write c squared, that component is squared, c squared, that component is squared, and c squared, that component is squared. And well, we can factor out c squared now, so this is u1 squared, u2 squared, up to un squared. And see, remember that if you have two numbers multiplied under the square root, those you can separate the square root for each one. So we will have c squared, square root of c squared, and this guy here. A square root of a number squared, we have to be very careful. It's not just c itself, it's absolute value of c. For example, try -1 squared is the square root of 1, which is 1. It's not -1 itself. It is absolute value of -1. And this is where this absolute value of c comes out. And this is, well, by definition, length of u. So that is how scalar multiplication and length of a vector have a relation. The second, the third property, which we will prove it later, it's called Cauchy-Schwarz inequality. Cauchy S-C-H Schwarz inequality. And it basically says that what is the relation between, so u dot v is a number, and how we can compare them with length of u and length of v. So Cauchy-Schwarz inequality we will discuss in details later. But here, what it says is that this u dot v is always less than, equal to length of u, length of v. Well, actually it is even better. Absolute value of that is less than u dot v. So this proof will come later. Proof will be given later. Watch the angle video. But I will use this one, Cauchy-Schwarz inequality, to find how the length and vector addition work with respect to each other. So this says that u dot v and length of u, length of v have a relation. This sums of lengths is always bigger than the length of sum. So this is called triangle inequality. And the reason we call it triangle inequality is obvious. You see, this is in 2 dimension. I can show you. This is U, this is V. And using the head to tail rule, we know that this is U plus V. And this is basically a triangle. And we know that in any triangle, planar triangle, sums of length of any 2 sides is bigger than length of the third one. And this is exactly what it says. Length of the third one, U plus V, is less than sums of the length of 2 other sides. Well, how do we prove this one? In the proof of this one, we will use Cauchy-Schwarz inequality. And let me just show it for you. So U plus V, you know that length of a vector is square root of U dot U. But we will use the other way around, like not the other way around. We will use this equivalent version of that this guy, length squared is U dot U. Okay, so I will start with length square instead of length itself. You will see at the end how we will deal with that one. And we know that this is UV dot U plus V. Now we have distribution property. So this we can distribute over that. So we get U plus V dot U, then plus U plus V dot V. We also have this distribution from the right, so it will be U dot U plus V dot U plus this one, U dot V and plus V dot V. This guy here, now we know this is U length of U squared. This guy here is V length of V squared. UV and VU are the same thing. This is commutativity. And what we can write is 2U dot V. U dot V is a number, and all numbers, doesn't matter what is that number, are less than absolute value of that number. So I can replace that one by its absolute value, but we may get a bigger number. So 2U, okay. The number here, it is this guy plus length of V squared. And while here now you see that we are in Cauchy-Schwarz inequality, instead of absolute value of U dot V, actually we can write it is less than 2 length of U length of V plus length of V squared. And well, remember this algebraic identity that A plus B squared is A squared plus B squared plus 2AB. Well, people usually write the other way around. It doesn't matter, that's the same thing, but just to keep you not to confuse you, I will write that way. So this here is the same thing. This is A squared. This is AB, 2A squared plus 2AB plus B squared. And that means that we have A, which is length of U, plus B, length of V squared. What we proved here is that length of U plus V squared is less than length of u plus length of v square. While these are two positive numbers, that means that we can find the square root of these ones, and then you get length of u plus length of v. And that is how we prove triangle inequality. Okay, so these were the properties, basically how dot product and length work, how sum and length work, how scalar multiplication and length work were three important properties. As a quick review, well, we did define what is dot product first. Sorry, length of a vector. We did define we did define what is distance of two vectors. We did some examples, and then we studied the properties of length.